All right, so we're going to talk some more about Newton's laws of motion. This time we're going to talk more, in fact, about Newton's first law of motion, which is commonly referred to as the law of inertia. We're going to find out why that is. You got to believe. All right, so inertia, according to Newton's first law, states that objects tend to keep on doing what they're doing. If they're moving, they want to keep moving. If they're sitting still, they want to sit still. In fact, the tendency of most objects is to resist any change in their state of motion, whether their state be sitting still at rest or in motion. Their natural tendency, think about it, their natural tendency is to object or to resist changes in their current state of motion, no matter what that state of motion is. So this tendency in their state of motion is described or called inertia. And that's why it's the nickname for Newton's first law. So inertia, by definition, is the resistance that an object has to a change in its state of motion. That's the official definition. So if you are following along, which if you're watching this video, then you're following along, you might want to have your worksheet open because a lot of the blanks you'll be able to fill out as we go along here. And we're going to stop and look at some videos, and there's some guided questions on your worksheet as well that you'll be able to fill out based on our discussion here. All right, so inertia, being Newton's first law of motion, declares that a force is not needed to keep an object in motion. You don't need a force to keep an object moving, contrary to popular belief. If you slide a book across a table and watch it slide, it'll eventually come to a stop. The book in motion on the tabletop does not come to a rest position because there is no force acting on it. It's the exact opposite. There is a force acting on it, and that force is friction, and that's what brings the book to a rest position. So really, it's not that we need force to keep it moving, and the absence of force causes it to stop. It's that there is a force acting on it, and it's the force acting on it that causes it to stop, not the lack of a force acting on it. So it's acting on it in the opposite way that we think it should be. So in the absence of the force of friction, the book definitely would continue moving. So think about if you put the book in space and you give it a little tap, it would just start to move very easily, low inertia in space, and it would just keep going the same direction and the same speed almost forever. Well, in space there is a little bit of friction, so it might eventually come to a stop, possibly, if that force of friction were able to overcome the inertia of the object itself. And we're going to figure out what that means here in a minute. But generally speaking, you could probably push that book a little bit hard and it would just keep going forever and ever and ever. That's in space where there's hardly any friction at all. Because without that force, there's nothing to bring that book to a stop. So it's the force itself, particularly in this case of friction, that brings the book to rest. And I know it's hard to believe, but there are still people that think that you have to have a force to keep something moving or it'll just stop. But that goes against everything that Newton said about motion. So let's watch a little video clip. I think you'll find this pretty cool, a little surprising, and it's only about 4 minutes long. So we'll watch this clip and then you can take a look at what comes after that.
Hello, my name is Bruce Shaney, and today I'd like to show a classic demonstration of Newton's first law. Now I have this bowling ball, and it's got a string attached to the top of it, and a second string hanging out the bottom of it. And what I want to do is support it on this metal bar. There we go. And as I hang it down, the first thing I notice is that this string is stretched very, very thin. Now my question is, if I were to pull down on this pencil, what do you think would happen? Obviously one of the strings is going to break, but the question is, which one? So let's see. Okay, top string broke, and that shouldn't come as a surprise. This ball weighs 6 pounds, it's very heavy, and so it's already applying a lot of force to that top string. I can do this again, and once again, if I pull down on the pencil, the top string breaks. Now I can repeat this all day long, but is there some way that I can actually get that bottom string to break? Top string breaks, I'm going to buy you a nice peanut for lunch. And if this bottom string breaks, you're going to buy a new one, is that right? So all I'm going to do is pull down on the string, and if the bottom one breaks, you owe me nice pulled it fast. Oh yeah, I did pull it fast. I still pulled it though. Why does that make a difference? If I take this pencil and I pull it quickly, the bottom string breaks. Now in some cases, if I'm quick enough, I can even break 2 strings down here while it was just 1 string up here supporting it. So I can determine which string breaks just about every time by how I pull it. But why is this? Now we can try a slight variation of this experiment to see what's going a little bit clearer. Once again, I have a brick. It has a lot of mass. And if I take the string and pull it, the brick moves. I can accelerate it slowly because it doesn't need much force. But if I try and pull it quicker, once again we see the string break because I'm simply trying to accelerate this brick at too high a rate of acceleration. The string simply can't apply that much force, so it ends up breaking. Now the idea of inertia is dependent on mass. It works very nicely with this brick. It has a lot of inertia. What about if we tried something lighter? So here's a styrofoam block. If I try pulling this slowly, it accelerates very easily. And if I try pulling it fast, well, let's see what happens. Oh, try it again. I can pull this as hard as I can or as fast as I can. It simply doesn't have enough mass to have enough inertia to break the string. So when I pull quickly against the mass of this bowling ball, inertia keeps that force from reaching the top string.
Okay, so I hope you enjoyed that video. Pretty interesting with the string and the inertia. So we know that Newton's law tells us that an object at rest stays at rest and an object in motion stays in motion with the same speed and the same direction unless it's acted upon by a force. That's just, we're reinforcing now Newton's first law. And so there are some, well, here's our exit ticket for today's exit ticket lesson. I want you to give an example of Newton's first law being applied. You can't use any of the laws that we've used today, but come up with your own example of Newton's first law being applied. And now what I want to do is go over the guided section, the guided notes. So I want you to just stay tuned, keep the video playing because I'm going to show you some objects, and on your worksheet you'll find a place to order the objects based on inertia. Now keep in mind what the gentleman in the video said. He said that inertia is based on mass. So the greater the mass of an object, the greater inertia it has. Okay? So inertia is the tendency of an object to either stay still or stay moving. So if you have a heavy object, one with great mass, it takes a lot of force to get that thing moving if it's sitting still. And if it's moving, it takes a lot of force to stop it. Okay? Think about a dump truck versus one of those little electric cars. It's a lot harder to get that dump truck moving. You need a bigger engine in it in order to get it moving. And you can put little tires and a little electric engine in an electric car, and it's easy to get that moving. Once you get them both up to about 50 miles an hour, it's a lot harder to stop the big dump truck. You need great big ginormous brakes in order to try to stop this dump truck from moving. And with the little electric car, you just need little brakes and it'll just slow right down because it doesn't have a lot of mass. So it has low inertia. And so that's what a lot of what he talked about in the video. So now I'm going to show you 5 objects, and you are going to list those objects in order of greatest to least inertia. Okay?
All right, so here are the 5 items. Obviously, it would be easier if you were able to actually pick them up, but just based on size and knowing what they're made out of, what do you think? So first we have a bucket of rocks, some pretty big rocks too. And we have a marker, a Sharpie, a ruler made out of plastic, pretty flexible plastic. We have a smartphone and a rubber band. So list them in order of inertia.